Cells in series and parallel. Physics for everyone welcomes you. In the last class, we have learned cells in series. Now we learn cells in parallel. Next class, we learn mixed combinations of cells. Cells in parallel connection is mainly used for getting more current. First cell, below which second cell, third cell and fourth cell. Good. In a parallel connections, all the positive terminals of the cells are connected to one point and all the negative terminals are connected to a second point. These 2 points forms the positive and negative terminals of the battery. Here you have 2 cells. First cell has an EMF of epsilon 1 and internal resistance R1. Similarly, the second cell has an EMF of epsilon 2 and internal resistance R2. These two are connected in parallel. Each one has a current. The first one has a current of I1. The second cell has a current of I2. The total current is IP. Now, this is the battery. The combination of 2 cells with internal resistance Rp and EMF EP, epsilon P is given. The current is IP. Let us go for a simple logical explanation. The first cell is short circuit. Then the current I1 is given by epsilon 1 divided by R1. Similarly, the second cell is short circuit and the current I2 is epsilon 2 by R2. Now these 2 cells now getting connected, right? Then the IP is given by epsilon P by Rp. Let us go for a simple Kirchhoff's first law. The total outgoing current equals total incoming current. So IP equals I1 plus I2. Let us replace IP by epsilon P by Rp and I1 by epsilon 1 by R1 and I2 by epsilon 2 by R2. In this equation, let us take 1 by Rp to the right hand side. So epsilon P equals epsilon 1 by R1 plus epsilon 2 by R2 whole divided by 1 by Rp. Epsilon P equals epsilon 1 by R1 plus epsilon 2 by R2 whole divided by 1 by R1 plus 1 by R2. This is nothing but 1 by Rp. So let us write these 2 equations once again here. Good. Now let us reverse the second cell. Once we reverse the second cell, what happened to the circuit? Look at it. The total outgoing current is IP plus I2 and the incoming current is I1. So we can write IP plus I2 equals I1, IP equals I1 minus I2. Now the EMF epsilon P will be equals epsilon 1 by R1 minus epsilon 2 by R2 divided by, there is no change in the internal resistance because of the reverse of one battery, one cell, 1 by R1 plus 1 by R2. 1 by Rp equals 1 by R1 plus 1 by R2. This is the first cell, second cell, third cell, fourth cell, fifth cell. Then all the negative terminals are connected and all the positive terminals are connected. These cells together in parallel combination connected to an external resistance R in series. Let n cells each of EMF epsilon 1, epsilon 2, epsilon 3, epsilon 4 and internal resistance R1, R2, R3, R4 respectively are connected in parallel and then in series with an external resistance R. Epsilon P equals epsilon 1 by R1 plus epsilon 2 by R2 plus epsilon 3 by R3 plus plus epsilon n by Rn divided by 1 by R1 plus 1 by R2 plus 1 by R3 plus plus 1 by Rn. Now Rp equals 1 divided by 1 by R1 plus 1 by R2 plus 1 by R3 plus dot 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 plus 1 by Rn. Let us highlight the important equation. For n identical cells in parallel, look at the diagram. Each cell has the same EMF epsilon and the internal resistance R. Now the equation becomes epsilon P equals epsilon into n by R divided by n by R. N by R getting cancelled equals epsilon. So epsilon P equals epsilon. The total EMF in parallel connection equals the EMF of one cell when all the cells are having equal EMF and equal internal resistance. So Rp equals 1 divided by n by R equals R by n. So Rp equals R divided by n, and Ip equals epsilon P divided by R plus Rp. Ip equals epsilon P is epsilon and external resistance R as it is plus the Rp as small r by n. Ip equals n times epsilon by n times capital R plus small r. Case A. If the internal resistance is much greater than the external resistance, then Ip equals epsilon divided by R plus small r by n. Here the capital R term is neglected. Then we get Ip equals n times epsilon divided by R equals n times I1. I1 is the current due to a single cell when R is negligible. Thus, the current through the external resistance due to the whole battery is n times the current due to a single cell. Let us highlight the point. Case B. If R, the internal resistance, is much less than the external resistance, then Ip equals epsilon divided by R plus small r by n. Here the small r term getting neglected, then we get Ip equals epsilon by R equals current due to a single cell I1. The above equation implies that the current due to the whole battery is the same as that due to a single cell when the internal resistance is much smaller than the external resistance. Hence, it is advantageous to connect cells in parallel when the external resistance is very small compared to the internal resistance of the cells. Now, parallel grouping of n non-identical cells. Now, let us remove the last two cells. Let us connect them in the reverse polarity. In a parallel grouping of n non-identical cells, if some cells in parallel grouping are connected with reverse polarity, then epsilon P equals sigma I equals 1 to n epsilon I by Ri minus sigma j equals 1 to m epsilon j by Rj whole divided by sigma I equals 1 to n 1 by Ri plus sigma j equals 1 to m 1 by Rj. Rp equals 1 divided by 1 by R1 plus 1 by R2 plus 1 by R3 dot 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 up to 1 divided by Rn plus m. Thank you, children.